Okay, so over the last, we're up to 2 weeks now. We've covered 4 topics, and we're now ready for really the essence of chemistry. Okay, up until now we've been talking about how to know our letters on the periodic table, right? Have I given you guys the analogy of my daughter learning her words? Like I have a 2-year-old and a 5-year-old. The first thing that you need to know in order to speak the English language and know words is you need to know your ABCs, right? What are the ABCs of chemistry? Periodic table, right? Before you can start to form words and sentences, you need to know all the letters of the alphabet, right? And so we've spent a couple of days really working on the periodic table and learning things like this, learning how there could be a sodium, what is sodium, 11? A sodium 11 with a 20 in the corner, and how that is different than a sodium 11 with a 19 in the corner and a 1 plus charge. We're talking about all those little nuances that are different between those. That's what we've been discussing so far. Give me 1 second. I'm going to disconnect my phone from the computer because it's giving me lag. Yeah, I can tell already. Disconnect. There we go. It's already faster. Okay, back to it. So these are your letters, okay? This is the alphabet of chemistry. Now, what we're working on the sideboard here, and some of you feel free to keep writing down the big flow chart because I could see it in your eyes as we were going through it. Some of you had this epiphany of like, I can name compounds with this thing, right? That's now figuring out how to do words. That's being able to take, say, sodium with a plus, chlorine with a minus, and going, I can name that. This is now going to be sodium chloride. Or whatever the compound happens to be, right? Now we're at the essence of chemistry, though, is we need to actually take our vocabulary, which is our letters and our words, and actually do something with it. Chemistry would be really boring if all we did all day is just name stuff. That's not chemistry at all, I gotta tell you. You need to have the basics, right? But it would be like if you're in band or music, and all you did all day is learn the notes on a scale. Sorry if you don't have any musical backing, but like just as an example, this is not music to do just this entirely. If I were to give you a worksheet with a clef of music, for those of you who know how this works, all right, and I put a treble clef here, so that's really bad. Now we're to, if I were just to ask you what note that is a C, by the way, yeah. Although you need that to understand music, if we just did that all day long, that's not actually enough. Does that make sense? So that's why I'm beginning my lesson by pointing out that we're now kind of at the stage where we can, that's why we're at the stage now where we can actually do something with chemistry. So we're going to begin now with chemical reactions. We're going to talk about what happens when we react chemicals together, which we've already discussed a little bit, because we've discussed the concept already of physical versus chemical changes. Okay? There are 2 types of changes. One's a physical change, where it's usually just a state of matter that changes, or if I rip a sheet of paper in half, or I crumple up a pop can. Is that really anything that's different fundamentally? No. A chemical change needs the formation of something different, something new. Often the word we use to describe a chemical change is that it's irreversible. I think I've used that concept with you guys before, right? Like, if it alters it, if it destroys it and makes it something new, that's a chemical reaction. That's our goal now. Okay? So the word that we use actually is no longer chemical change. Okay? We do talk about physical and chemical changes, but we actually prefer the word reaction. That's more of like a technical science word. Okay? So you could call it a physical change. You could call the opposite of that a chemical change. But usually we don't use that. We either call it a physical change or a chemical reaction. Does that make sense how we're going to use the vocabulary? Chemical reaction is the proper term. And it's basically when a substance reacts and creates something, keyword here, different. Okay? I think we know that concept, though. That's not new to us. Now, what we've discovered is that there are some similarities that all chemical reactions have. And one of them is involving the concept of energy. All chemical reactions, you can read this here, involve what's called energy flow. And we can actually categorize our chemical reactions into one of 2 main categories. Maybe you know this vocabulary. If not, it's going to be on my future slides here. They're known as either exothermic or endothermic reactions? Can you guys give me a quick show of hands? Has anybody ever heard the words exo and endo? Cool, okay, so you learned about this maybe a little bit in grade 9 then? Awesome. Okay, we'll give you the less detailed version. Exothermic reactions involve energy that is released in some sort of format. The way I remember this is that this is energy that is exiting. Okay. Like, for example, see how this thing is on fire right here? Energy is being released in some form. Light, heat, something like that. And if we were to write out a classical reaction like this one right here is a classic reaction type of thing here, we could say that energy is being produced in some way. And honestly, that's a really important thing nowadays, just from a global point of view, because we need energy. We need to produce energy. Alberta is known for its oil and gas industry, right? So energy production is anything that's exothermic. The other category, sorry, I have one more slide before I get to that. The most common example of exothermic reaction is combustion. You've probably heard that term before. It's literally where something is blowing up. Yeah, it goes kaboom. And there's some common themes to it. Combustion always involves oxygen reacting with a substance and producing energy. Here's a good place for a little bit of a side note, a little side lesson while we're here. You know how we've been working on, say, a square on the periodic table, for example, sodium. And we've been discussing how this corner down here is protons. This corner up here is mass, protons and neutrons. This corner up here is a possible charge. I haven't focused on this corner down here a whole lot recently. That corner there is known as the allotrope. And we're now going to need to focus on that a little bit more, because when we write out chemical equations, chemical reactions, we need to know whether sodium comes in a group of 1 or in a group of 2 or etc. And the reason I point that out is that right here, this is oxygen. But you might notice that it's not just oxygen written with the 8 in the corner and the 16 and the 2 minus. It's written in its allotrope form. What I just crossed out is its isotope form. O with a 2 in the corner implies that oxygen just naturally comes in a 2-pack. I gave you guys the toothbrush at Costco analogy, right? Right? Sometimes when you need to go buy an item, you can buy them single. Sometimes you have to buy it in a group of 2. And you're like, oh, I didn't want 2 of them, but apparently it only comes in a package of 2. That's an allotrope. And this number down here in the bottom corner indicates that. Understanding why oxygen comes in an allotrope of 2 is third-year university chemistry. So for right now, is it just okay just to accept that? There are certain things that just come in 1s, 2s, 3s, 8s. And we'll write a list down if we need to help us remember it. So anyways, that's my brief side note here, is be aware that when we do this, we might have to start putting the 2 in the corner there for certain things. Okay, here's the opposite of exothermic. Back on track here. Exothermic's opposite is endothermic. So endothermic reactions are reactions that require energy to run. And I remember this by the word enter. You need energy to come into the reaction to make it work. The picture on the page here is a good one. It's a cold pack. There's no such thing as cold, by the way. Has anyone ever shared this with you? Scientifically, there's no such thing as cold. Cold is just the absence of heat. Ever heard that before? There's also no such thing as dark. Dark is just the absence of light. There's some things that truly have opposites, like left and right. But scientifically, there really is no such thing as dark. It's basically, dark just means that there is no light, right? There's no such thing as cold. Cold just means that you don't have heat. Anyways, we feel them as cold, though, because what's really happening when a reaction feels cold to you is it's sucking the heat out of an object. Right? Anyone ever have a parent that says, close the door, you're letting all the hot air out? That is actually true, if in the wintertime. But if you have a parent who says, close the door, you're letting all the cold air out, don't be too cheeky when you say this. That's not actually how it works. It's not actually that the cold air is being let out. It's that the warm air is being let in. That makes sense? Yeah. Because it's actually heat that's transferring from hot areas to cold areas. Okay, anyways, let me give you one more example of an endothermic reaction. Baking. Why is baking in the oven an endothermic reaction? Why is baking in the oven an endothermic reaction? Yeah, if you didn't hear that, the heat has to poof everything up. Yeah, let's say you mixed a cake, right? You beat the eggs, you have all the batter, the flour is all ready to go, right? And you just let that cake batter sit on the counter. Nothing happens, right? But if you add some heat to it, here you need to add the heat. The cake absorbs the heat from the oven and makes your cake poof up. Well, for lack of better words, I like it though. That was good. Yeah. Okay, long story short, here's what I showed you on these two slides. I need you to categorize chemical reactions into one of two. It's either endo or exothermic. It either produces energy or it requires energy in some sort of format. Okay, so let's talk about this slide here for a second here. I'm going to actually do something I rarely do. I'm going to read directly off my slides. You might have noticed I rarely do that, but read along with me here. So burning wood then seems to create thermal energy, right? Because this would be exothermic, wouldn't it? Burning this wood right here would seem to produce thermal energy. Does this break what's known as the law of conservation of energy? Maybe you've heard that before. And the answer is, well, no. There's energy present in the bonds of, and this is the key vocabulary we're going to start working on, reactants and products. Reactants and products are all of the items that are being used inside the chemical reaction. And those bonds are actually what helps hold matter together. That's really the key, is that there is actually energy inside those bonds, right? Here's one of the chemicals we should know how to name a little bit. This is carbon dioxide. It involves carbon being bonded to oxygen. And inside this bond right here, there is actually energy keeping it tied together. Think of it as glue or a rope or something like that, right? So anyways, there is energy inside of these bonds, and as you break these bonds, it can then release them. So it's not like energy came out of nothing. The reason why there's energy coming out of this wood as it's burning here is that bonds are literally being broken, and you can read that here. When a chemical reaction takes place, bonds break, causing the energy changes. So it's not like the energy comes out of nothing. It comes out of the bonds. Okay. So here's a summary then of what we just discussed. The two possibilities, hopefully it's clear. Exothermic, you lose energy. Endothermic requires energy. Is that more or less review? A little, maybe a few additions here. Okay. So then the question is, well, if we're going to start talking about actual chemistry where things are reacting and changing, how are we going to know whether it's a chemical change, a physical change, there we go. How will we know if it's a physical change or a chemical reaction? And here's a bit of a list going on here of some of the common characteristics that you'll notice during chemical reactions. You probably know some of these. For example, if you find some sort of new substance with a new property, we must have changed bonds. We must have changed what's going on. If there's a smell or a color change or something has a new density, it underwent a chemical reaction. If you can see the flow of energy through detecting a temperature change, you must have had a chemical reaction. Maybe there's a phase change, things like bubbles being formed or a solid that appears. All of those would be evidence of something that's a chemical reaction, something new being formed. We're actually going to do a lab on this, I think, early next week, where I'm going to combine some chemicals together, and our goal is going to be to note some of the observations we have and figure out whether or not it's a chemical reaction or a physical change. So let me give you a couple of examples. Let's say that I take a piece of paper and I light it on fire. Physical change, chemical reaction. Lighting a piece of paper on fire. We've done this one before, right? Isn't that going to be a chemical reaction? But like, here's some of the proof. Well, now we saw the energy change because we could see it being lit on fire. We probably could smell it. What about color? Piece of paper was white, now it's going to be black and burnt, right? Let me give you a different example here. What if I take that same sheet of paper and I crumple it up? Did it change its color? No. Does crumpling it up make it smell? No. Does it have a new melting point? No. Okay. So we'll actually do some examples of this in a lab. Okay. Now, one of the other things when we're talking properties then is we'd like to know what are the properties of the reactants and the products. You guys know those words, reactants and products? What we start with and what we finish with? We'd like to know some of the properties of ionic and covalent compounds just so that we know what is normal. Okay? So again, this is one of those sorts of things where I don't need you to memorize this. This is not a list where it's like it's going to be on a test somewhere. You can always look back at your notes. But we've discovered that there are some very similar properties for things that are either ionic or covalent. And I've just got them on a list here. So let's walk through them. If you have an ionic compound, chances are it has a high melting point. It means that it's very, very hard to turn it from a solid back into a liquid. Okay. Let me give you an example. Salt. Salt is a classic ionic compound. It's NaCl. But if you were to take salt and put it on the stove, like put it on the like on the grill of the stove or something like that, you're probably going to burn it before you melt it into a liquid. You ever seen liquid salt? I mean, it's actually possible, but it takes like hundreds of degrees Celsius to turn it into liquid salt. Normally, salt is in a solid format. Does that make sense? So if you were to add heat to it, if it burns before it melts, it's probably ionic. Can I say that one more time? If you were to add heat to it, if it's going to burn before it melts, it's probably ionic. Let's pick something different. Water. Can I burn water? Really? Or are you just being silly here? Can you burn water? I've never seen that before. I would love to anyways. Because, I mean, what happens when you add heat to water? Does it light on fire or does it start to boil? Right. Do you guys see the difference between the two there? Ionic compounds in general will like to probably burn before they boil, whereas covalent compounds, like water is, by the way, water is a covalent compound, it will tend to boil before it ever lights on fire. So that's a common property of ionic ones then. Here's another one. They like to keep crystal shapes. Since we were talking about salt, salt likes to get stuck in little crystals. Okay? And like we would see those not as flakes as much, but as like little granules. If I use the word granule, do you kind of get what I'm saying there? Right? Like a grain of salt. Yeah. That would be in a crystal format. So that's a very common property of anything ionic. Think of salt. That's a good example. Here's two more properties of things that are usually ionic. One is that they're soluble. It means that if you add them to water, they have the ability to dissolve. Okay. You ever added like Kool-Aid crystals or iced tea crystals to water? And then you stir them all up? Now, sometimes there's a few left in the bottom of the container, but in general, if you can stir it up and like there's no more solids that you can see, it's all kind of consistent, and it's a solution, then it's probably ionic. When you're drinking Kool-Aid, can you taste all the little granules of Kool-Aid anymore? If you don't mix it up properly, sure. But otherwise, that would be the worst Kool-Aid in the world, wouldn't it? Anybody ever made pudding before? And it hasn't been stirred very much, and there's a little bit of like chunkiness to it, and it's a little right? That's kind of what I'm describing the opposite of here, is that it should dissolve very nicely if it's ionic. Okay? There's actually some reasons for it. We don't really care about that too much right now, but in case you want to know the reason, it's because water is a polar molecule, and it can pull ionic compounds apart. Not going to be on a test, because I'm not even doing tests, so don't stress over that, but that's the reasoning. The last thing is, usually ionic things like to conduct electricity. Okay. We did a little conductivity test the other day when we did our lab, and yeah, as long as it conducts electricity, it's usually a pretty good test it's ionic. Well, the opposite of that is then properties of molecular compounds. Remember how ionic compounds are a positive and a negative? Molecular compounds are a negative and a negative. And in the most, now by the way, side note, this is not a hard and fast rule. This is not a 100% guarantee, bet your life on it, but like this is a general sense of things. The general sense is whatever makes something ionic, it's the exact opposite property for covalence. So like covalent things have a low melting point in general. Let me give you an example of one that you'll be familiar with for this. Carbon dioxide is a molecular compound. Okay. How do I know it's molecular? Well, if we follow that little flow chart there right there, carbon and oxygen are both your nonmetals. They're both negatives. What state of matter is carbon dioxide in? A gas, air, a gas format, right? So, does it have a low melting point? I know it's kind of weird to think of, but like not only has it melted out of its solid phase and into its liquid phase, it's actually gone even further. It's actually boiled from the liquid phase into the gas phase. And that's kind of weird for us to think of, because I wouldn't think of carbon dioxide as needing to boil. But like it has already boiled. There's no way, like it's really hard to get carbon dioxide back to a solid. Does that make sense how I'm phrasing that? So because of that, most molecular compounds are usually gases. Is usually their state of matter. Most molecular compounds are usually gases because they don't usually stay in a solid format. And because of that, their crystals are very weak. Let me talk about another molecular compound you're familiar with, water. Now, water is probably the best one to discuss because I think all of us can envision it in all three states of matter, right? I think we know what water looks like solid because that's ice. We know what water looks like in its liquid format because that's what we normally call water. And you guys all know that you can evaporate water as well, right, into a gaseous form, right? Well, water is a good example of why covalent compounds have very weak crystals because they snowflake. What happens when, like, say, water turns into a solid, as an example, when it gets cold out here in about 3 weeks, and the first time someone goes up to their car and there's frost on their windshield, right? Wouldn't that be water in a solid form? How hard is it, though, to get the frost off your windshield? I mean, it's a pain. Obviously, it's annoying. But, I mean, you can take a credit card and scrape it off. Does that make sense? Which means it flakes. If it flakes, that's different than it's remaining in its crystal format. Does that make sense? Imagining frost on your windshield versus salt granules. There's a difference in terms of molecularly how they fit. This would be a picture of what molecular compounds might do versus this one right here is a picture of like a granule of salt. And this one's really stuck together quite nicely. Whereas this one right here, you can like flake this piece off and you can flake this piece off, right? So they bond differently. So they're much weaker. Okay, and then the opposite property still holds for molecular compounds. They're actually very non-conductive. Okay, ionic things conduct electricity. Molecular things don't. Which then leads to the question, hang on, Chris. Isn't water the most dangerous thing to like have electricity run through? You probably heard the whole thing like don't drop a toaster in the bathtub with you because you'll electrocute yourself, right? So here's the reason why. Yeah, don't do that. Okay, let's talk about why though. Water in its pure format, if you just had pure 100% water, which we actually have a name for, we call it distilled water, it won't conduct electricity. And I'll show that to you in a test. However, tap water, water that comes out of an ocean, water that comes out of a lake, almost all water has some impurities dissolved in it. Okay. For example, if you drink tap water, Lethbridge still fluorinates their tap water, which is to try to help prevent cavities in kids' teeth, right? Well, if there's anything dissolved in the water, then water's not pure anymore, then it will conduct electricity. And so almost all water has at least something dissolved in it. I challenge you, oh, hey, there's one right here. This is perfect. Next time you guys find a water bottle, just a basic water bottle like this, look on the back of the label, and it's not going to say that it's pure water. There should be a list, normally, of some salt content. I found it here. It says there's a mineral salt content here of 97 parts per million. All that means is that it's not 100% pure water anymore. It means there's something dissolved inside like this. Okay, so long story short then, water, although water is technically a molecular compound, if it's pure, it wouldn't dissolve or it wouldn't conduct, but usually there's stuff inside our water, and so therefore it does conduct. Here's kind of a picture of a test of that. Often the test is that you like run a light bulb through it. This is kind of cool. You can see how the light bulb's got a wire right here, runs a wire through to here. You see how the two prongs though aren't touching? Right? If the two prongs don't touch, but the light bulb still works, it means it conducts electricity. And long story short, it's a good test then as to whether it's covalent or ionic. This thing right here, NaCl, is ionic, so therefore the light bulb works really well. Here's the only problem with that. This is not like a one or the other rule. This is a more or less a general consensus, but like there are exceptions. Okay, so don't like, bet the farm on it. You got what I'm saying? But it's a general rule. Okay. Now, we're talking about water. I've got to continue with it. I guess I got to it a little earlier. There's actually some special properties that are nice to know about water. Again, don't worry about memorizing it. We'll always be able to look at our notes, but here are some special properties of water. Water is one of the most unique substances that we've found in the entire universe. In fact, it's one of the reasons why you sometimes hear these claims where it's like, water's been found on Mars, or water's been found in like some random planet or moon, because if there is going to be life, as we know it somewhere else in the universe, we guarantee it would require water. Okay. So I've got a list of some pretty cool properties right here for water that are very special about it, that are actually the properties that allow life to be maintained. If any one of these properties didn't exist for water, human life wouldn't work. So it's incredible how that works. Here's the first one. The boiling point and melting point of water are really high. Water actually has a relatively high boiling and melting point. Okay. We just said that water was a molecular compound. Okay, they're both nonmetals. But what is the natural state of matter that we normally think of when we think of water? Liquid. But almost all molecular compounds I mentioned otherwise are usually in a gas format. That's very strange. Here's why that is so important to us as humans. Our sun heats up our Earth at around, let's say 20 degrees Celsius is a pretty median temperature for most places on Earth, maybe 10 degrees Celsius. Well, if water's melting point and boiling point weren't at 0 and 100, we might live in a world where we have too much gas water or too much solid water. Does that make sense? But we need to ingest liquid water, right? A source of water is super important to the human body. So it's actually really fortunate that water's range goes from 0 to 100 from melting to boiling, because most other covalent substances, that's not their range. So that's really one interesting one. Okay. Here's another one. Water is able to absorb a huge amount of energy before its temperature changes. Okay. Here's why this one's really important. Global warming. It's so big in the news nowadays, where we hear about, okay, the Earth is heating. One of the reasons why the Earth is not just like bursting into a ball of flames is because there's so much water on the Earth, and water is a great heat sink. You ever heard that phrase before, a heat sink? You can basically heat up water and throw a bunch of energy into it, and it hardly raises the temperature, which is good for us. Other planets at a similar distance to the sun than us would be much hotter. But because we're made of so much water, first, the water doesn't evaporate. That's perfect. Thank you for not letting the water evaporate. 2, the water can absorb the energy from the sun, and it doesn't make Earth unhabitably hot and make it be like 50 degrees Celsius. Does that make sense? So, here's another interesting property of water. Water has a concave meniscus. What that means is that water has the ability to kind of like bend when you see it on the surface of like a, I don't know how you describe that. Have you guys seen this thing before here, where water has the ability to kind of like bend a little bit there? And this we're going to learn more about in our biology unit, but due to this property here, water is actually able to move itself up a plant. Think about how plants grow. Where do you put the water in a plant? In the roots. But the water needs to find a way to get from the roots up to the rest of the plant. And there's not just like some magical elevator inside there that takes the water from the bottom to the top. It actually has the ability to do something called capillary action. We're not going to spend too much time talking about that right this second, but the short version of it is that water has the ability to, rather than stay flat, it actually has the ability to kind of cling up the sides of containers, which is really useful. All right, keep moving on here. Number 4, ice floats in liquid water. Another huge important one for human life. Because if it wasn't for the fact that ice floats in liquid water, our polar ice caps would be on the ocean floor. Well, no, they're floating, right? But think about how that affects the geography of Earth. We have Antarctica and Greenland, 2 massive bodies of ice that are actually floating on the surface of the water, right? Normally, things that are in a solid format don't float on top of things that are liquid. Stay with me, people. Take a marble, put it in water. It drops and sinks to the bottom, right? Take a rock, put it in water. It sinks to the bottom. But ice, unusually, actually expands as it freezes. And that's the reason why it floats, by the way. The reason why it floats is that ice expands while it freezes. This is weird because every other compound, when it freezes, actually contracts and gets smaller. You learned about this in a previous science class where when you heat something, it kind of enlarges and it gets bigger a little bit. Like that's what a hot air balloon does, right? You add heat to a hot air balloon, it expands. Water's weird. You freeze water and it expands. Okay. And here's the last one. Water has a high surface tension. We don't notice this all that much, but like there are like some bugs that can actually literally walk on the surface of water. And one of the reasons why is that there's so much clinginess between particles. They're called hydrogen bonds. Okay, I have one last thing we need to talk about here. Since we're talking about the nitty-gritty of how are we going to talk about all the chemicals that we're going to be reacting here, the last thing we need to discuss is whether or not something is a solid, liquid, or gas, because when we write these compounds from now on, we're no longer going to just write NaCl. We need to write afterwards a small little bracket right here, a state of matter. We have to include a state of matter. It's super important. To me, it's like punctuation when you're writing a sentence. Sometimes you have to end in a period or a comma or a semicolon or an exclamation mark. It makes a huge difference when you're actually performing chemistry to know whether or not you're working with a gas, a liquid, or a solid. So let me give you some basic rules. Since we've now learned that ionic compounds have a very strong structure to them, in general, put ionics as a solid. So if you wrote an ionic compound, write it down as a solid. However, what we're going to finish off our class with is sometimes we add these things to water, and then the question is, what happens in water? Do they dissolve in water? Because if they do dissolve in water, we call them AQ for aqueous. Okay. If they don't dissolve in water, we write an S for solid again. If you have a molecular compound, then it really just depends on the size of the molecule. In general, most of them are gases. Almost all molecular compounds are gases. But there are some that can actually be liquid or solid. As an example, beeswax is actually a solid. How will you know this? You really won't after 3 weeks of chemistry. Here's what I ask of you. Take a logical guess, okay, as to what you think the state of matter is. If you were to write down carbon dioxide as a solid, I would probably point out that doesn't seem very logical. Okay, give me one sec here. But if you were to write down water as a liquid or water as a gas, you know what? It probably could have been either one. Does that make sense? Yeah, question. Yeah. Yeah, dry ice is, oh goodness, where do I start with dry ice? Because it's really not like water in that same format here. Why don't we talk about that one later if that's okay. Just because I've only got 5 minutes left, I want to show you one more thing. Yes, there's another one, yeah, because nitrogen can be in a liquid format, but you have to drop the temperature to like minus 200 and something degrees Celsius. Yeah. Okay. Here's the last thing I need to show you. There is one application we need to work on. I think it'll work best if I just flip to this slide right here. There is a table that's in your data booklet that will help you figure out whether or not an ionic compound dissolves or not. It's a really easy table to work with. We'll do a little practice on it over time, but here's how this table works. Let's say that you have an ionic compound. What you need to do is figure out where your anion in the compound lies up top here in the top chart. And then it either falls into the category of something called very soluble or slightly soluble. Very soluble means it dissolves, and we write the AQ afterwards. It stands for aqueous, means it dissolves. But there are some things that don't dissolve well in water, and we write an S afterwards for solid. Let's try a couple examples, and then this is actually it for our lesson. Here's the question. Do we think that KCl will dissolve in water or not? Because let's say we write out the formula KCl, and we're trying to figure out what state of matter to put afterwards. Okay. You can then look at this table here and look along the top for your anion. What was our anion in KCl? Cl. Okay, so now we're looking in this column here. Somewhere in this column here we're looking. If it fits in the bottom category here, we'd write a solid. If it's anything else, we write AQ. So what fits in the bottom category? Well, if you combine copper, silver, mercury, lead, or thallium with chlorine, it would be solid. But otherwise, it fits into the most category. So based on how this chart works, when you're writing a state of matter, you would say that KCl should be aqueous. And that would be a good indicator so that you're not just randomly guessing what state of matter to use, but you kind of have a little bit more information. Okay? It's a pretty decent chart for that. Let's try a few more random ones in here. Let's try the next one, CaCO3. So you just wrote out CaCO3, you named it, but you're trying to take a guess as to okay, what should I write here? Use this chart. Find your anion. Okay, so where's your anion? CO3. Here it is, CO3. Everybody able to follow that so far? Okay, so then just try to figure out where calcium fits. Is calcium going to be here, or is calcium going to be here? Well, okay, it says group 1 ions fit here, but calcium is group 2. It also says NH4 is here. So I think calcium fits into this bottom category here. So that means that when you write it out, the punctuation you would use is that this thing is most likely probably a solid. Does that make sense? So all you need to do is have access to the chart and kind of practice a few. So let me do 2 more, and I think then we should be able to call it a day. Why don't we try this one here, CaSO3. So if I want to look for CaSO3, first I have to find my anion, which was SO3, which is right here, actually. It's in the exact same column. So where does calcium fit? I think we already ruled out the top half of the chart, didn't we? So by default, calcium must fit down here. It must be solid. I would write it as CaSO3 with a solid. Okay. Let's try one last one, and then if you need practice, I can get you practice. Let's try CuCl. So if we're going to do CuCl, just so we remember what we're looking for, first find where your anion is. Your anion is right here, Cl. We just got to find where copper is. Ah, look, hey, copper's down here, and this is the copper 1 version, right? Because there's Cu plus 1, Cl minus 1. So the copper 1 is down here, so I would write a solid next to this one. As a side note, let's say it was CuCl2. Well, this would be chlorine with the 1 minus, but this must be copper as the 2 plus version, because copper can be both plus 1 and plus 2. Plus 1 is down here at the bottom, but plus 2 isn't. So copper plus 2 must be up here. This is really weird. Copper chloride this way is solid. A different copper chloride is actually aqueous. Okay. So here's what we accomplished today. We were more or less talking about properties of compounds for one reason. The one reason is now when we're using this flow chart right here to figure out compounds, we can add one subtle little thing to the end of it, a state of matter. Okay? Do your best. Okay? Sometimes we don't know for sure, but you're either going to write solid, liquid, gas, or aqueous, depending on the scenario. Hey? For which one? Oh, okay, cool, thanks. Questions? Okay. Write a reflection on this as well, and you guys are free to go, I guess. So, Bell should be going any minute here. Thanks, everybody. We'll talk again tomorrow. Yeah, it was nice, eh? Laser hands. Love it. Okay, if you do have questions, make sure you ask, okay? Or ask them in the reflection.